So here we're going to do problem 20 in chapter 5 of Marion and Thornton. We have a disk that has a constant density sigma, which is the mass divided by the area of the disk. So that's going to be the mass of the disk divided by pi capital R squared, given that capital R is the radius of the disk. Our goal is to first find the gravitational potential phi at this point up here, P, that is a distance z above the center of the disk, and then to find the z component of the gravity field, which would be minus the derivative of phi with respect to the z coordinate. So the way we do this is that we are going to say that dm is sigma times dA, and we want to work in cylindrical coordinates. So we'll write that as sigma times s ds d phi, where s here is some radial distance to some point that is sort of in the middle of the disk. And then our squiggly r vector, our separation vector, magnitude, is going to be the square root of z squared plus s squared, and we're going to use that over here. And then for dm, we will have this expression. And so our gravitational potential phi is minus g times the integral of sigma s ds d phi over the square root of z squared plus s squared. And so this is a double integral. The s integral is going to go from 0 to r, and the phi integral is going to go from 0 to 2 pi, because we're going to go all the way around the disk. So that's the 0 to 2 pi in the phi direction. And we're going to go from 0 to capital R, the final radius of the disk, when we're integrating over the radial coordinate with a s. And so if I do the phi integral first, since there aren't any phi's present, that just pulls the 2 pi out. So I'm going to have a minus 2 pi sigma. That was a constant. I can pull that out of the integral. When I've done just the phi integral, s ds over the square root of s squared plus z squared. So now this z is our height, where we're going to have as a final variable. So our phi is going to end up being a function of z, how high we are along this central axis. We can see if we can do a u substitution here. We can let u be s squared plus z squared, and then du would be 2s ds, and that's convenient because s ds is present in the top of the thing. So the integral of s ds over the square root of s squared plus z squared would be equal to 1/2 the integral of du over the square root of u. And so the integral of du over the square root of u would be, with a half out front, would simply be I think I've done that right, would simply be u to the 1/2 power, right? So if I take the derivative of u to the 1/2 power, I would pull down the 1/2. And so what we have for phi is minus 2 pi sigma g times, now, so if I go back up here, this would be the square root of s squared plus z squared. So this bit of the integral is this 1/2. So I'm going to get 1/2 from this integral, and I'm going to get a square root of s squared plus z squared. I'm going to evaluate that from 0 to capital R. So the integral of s ds over that square root gives me 1/2 of, oh no, I don't need the 1/2. The 1/2 goes away when I do the integral. Just gives me that much of it. Yep, so that looks right now. And so I need to evaluate here for s from 0 to capital R. So I have minus 2 pi sigma g times the square root of r squared plus z squared minus essentially the square root of z squared, and I'm simply going to write that as a z. So I'm going to say that phi is 2 pi sigma g times z minus the square root of r squared plus z squared, if I have done all of my algebra correctly. Okay. So now what I want to do is compute the z component of the gravity field. So that's going to be minus the derivative of phi, this capital Phi, with respect to z. So I could have kept that minus sign then. So now I've got minus 2 pi sigma g. The first derivative of z is 1. Now I have minus 2, I'm going to get minus z over the square root of r squared plus z squared. Because when I take the derivative of the square root, I would get a 1/2 times all the stuff, that square root would go into the bottom. Then I take the derivative of the z squared in the top, and I would get a 2z, and that would cancel with the 1/2. So as a vector statement, I can say that g vector is minus 2 pi sigma g times 1 minus z over the square root of r squared plus z squared z hat. And so since I have mass here, and so this is along the z-axis. If I had mass here and I'm up at some point P along the z-axis, then the g vector is clearly going to point downwards towards the mass, which is why I have this minus sign. If I look, z divided by the square root of r squared plus z squared, this part here is going to be less than 1. And so what's in the parentheses is going to be positive. So I'm going to have 1 minus some number less than 1. If I put in z equals 0, I would be right on the axis of the disk, right in the center of the disk, and we get g is equal to 0, which makes sense because at the very center of the disk, the field would cancel out. And then if I go very, very far away and I do a Taylor series expansion, I'll see that I should be able to get something that looks a little bit like a point mass. So we'll stop there.